Have the slide of Vivek's introduction. He is going to talk about artifacts and pitfalls. So some interesting images. Let's see what he has to.
Okay, so my topic has been about artifacts, no conflict of interest to declare. And I will be using images from this article, and I have taken permission from Sharik, who's been very kind to share his images and cartoons because it was not possible without this. So the ultrasound artifacts, basically, artifacts are something which are not there, but we see that they are there. And they can be classified into two types. The ones which arise out of the assumptions of physics, which we make while doing an ultrasound imaging. And the others are the ones which arise when there is interference by an external electronic device or equipment. Very simple, ultrasound waves, when they hit the tissues, there are three types of interactions. Either they are transmitted, that means they move ahead in a straight line, or they are refracted, that means they move ahead but at an angle to the original beam, or they are reflected, that means they are sent back to the transducer. Now let us look at what are the assumptions when we start doing ultrasounds and echoes. The first is that pulses and echoes travel along a straight path. Echoes return to the transducer after only one reflection. Echoes originate only from the main transducer beam, and pulses and echoes are attenuated uniformly by all tissues, and pulses and echoes travel at a uniform speed. So these are some cardinal 5 assumptions we make before we start imaging. And violation of any of these assumptions leads to generation of false images. So when we look at artifacts due to violation of assumptions, we can classify them, and I have put the whole lecture in a very practical perspective. False images which appear below the true image, and false images which appear by the side of the true image. So if we have a false image below the true image, the artifact can arise out of what is known as a reverberation or a mirror image or an acoustic shadowing and enhancement. And if we have a false image by the side of true image, we have this due to either what is known as a beam width artifact, a side lobe artifact, or a refraction artifact. So what are reverberation artifacts? If we look on the left side of the screen, this is the transducer, this is the object reflecting it. Here it goes the beam, here comes back the echo. It is one round trip, and the time is calculated for the one round trip. But many a times we have beams which come from the transducer, go to the object, and keep getting reflected again and again. Or we have a second reflector, a strong reflector, which keeps reflecting these beams. So the more the number of reflections, the longer the time it takes for the beam to go back to the transducer, and it is interpreted as if that particular reflector is much below the original reflector. So keeping it very simple, single reverberation artifact, this is typical one round trip. But if you have two round trips, the ultrasound will sense the distance as twice as deep because the time taken for the return trip was twice as long. And this is the generation of the reverberation artifact. So what are the strong reflectors? These are the things we have to be very cautious. Aorta, especially calcified aorta, calcified structures, and implanted devices. We start with the example, single reverberation artifact. The violation is that there is one reflection only. Here, there are more than one reflections. And if we look at this view, short axis view, we see that the cavity one here is the left atrium, and this is the transducer. And at the wall between the left atrium and the left atrial appendage, there is a reverberation which takes place, which gives rise to a false image in the left atrial appendage. So this is the true image, this is the false image, which is twice as deep, and this gives the false illusion of a left atrial appendage mass. So it's twice the distance, and the problem is it leads to false anticoagulations, and the resolution is use multiplane imaging in TE, and you'll find that this doesn't occur. It occurs only at a particular place and a particular angle. Another common example is single reverberation artifact is in the ascending aorta, the long axis view of the ascending aorta. We see this is the pulmonary artery, and we see that there is a reverberation here which causes a flap-like structure here in the ascending aorta. And this leads to false positive diagnosis of Stanford type A. But if we put a M mode, we will find that this flap always moves in parallel to the shadowing flap. And this many a times has led to sternotomies which could have been avoided. And one of the simple bedside techniques is to use a M mode for intimal flap motion. You will find that this intimal flap motion is exactly parallel to the motion here. Complex reverberation artifacts are, well, something more than simple, and I'll just go through it. So there are two closely placed strong reflectors. So if we have a prosthetic mitral valve, so the leaflets there, they keep reverberating, so they keep reflecting from one to the other and it goes back to the transducer. So there are two closely placed strong reflectors, multiple round trips, typically seen with mechanical valves, surgical clips, and catheters. The problem is that not only it shows false images, it obscures the left atrium and you miss out on the MR jets. And the solution, of course, is multiplane transesophageal echo. Another example of complex reverberation artifact is a simple thing like a pacing lead which goes and you just see the myriad of colors it produces. So we have to remember that reverberation artifacts are not limited to grayscale. They can occur in color and it looks like a carnival. Coming to mirror image artifact, in mirror image artifact, the violation of the principle is that there is one reflection only and there is a linear path. Both the principles are violated. And what happens is if you have a strong reflector, many a times the beam, instead of going straight to the transducer, when it finds another strong reflector nearby, from the second reflector, it comes to the first reflector and then goes back to the beam. And the ultrasound thinks that this distance is particularly here. So we have the true image here as an anterior mitral valve leaflet, and we have a mirror image here as an inverted mitral valve leaflet. So we should know what are the strong reflectors, the pleura and the pericardium. Be very careful. Ultrasound beam is reflected back at an angle. It produces an inverted image. And the more important thing is the inverted image moves in a direction which is opposite to the original structure. So the question here is, which is a true image? It's easy to make. The true image is, of course, much more nearer and much more clearer. And the resolution is again very simple. Change your scanning plan and manipulate the incident angle. One of the common problems in this mirror image artifacts is the duplication of vessels. This we have all experienced, the IVC, the true image and the false image, and the reflection is coming from the liver margins. Duplication of vessels, and it leads to false diagnosis of dissections, especially in carotid and abdominal aortas. Resolution is very simple. Change the scanning plane and manipulate the incident angle. Well, I could not get what is known as a mirror image artifact and the concept of pseudo MR from my recordings, but it is very clear that when you have a prosthetic mitral valve in place, it acts like a mirror and the LVOT flow is mirrored onto the LA and it gives you a false sense of a MR jet in LA. But actually what you do is that you put a pulse wave Doppler and you will find that the timing and the velocity of this jet is actually identical to the LVOT flow. And moreover, there will be a gap between the prosthesis and the so-called MR jet. And that is the concept of pseudo MR. Now we come to acoustic shadowing. We are all familiar. The principle which is violated is that the beam uniformly attenuated by all tissues. Every tissue is different. There are tissues which are strong attenuators, which attenuate at more than 0.5 decibels per centimeters per second, especially the ones which have a lot of calcium prosthetic material and things like silicone breast implants. And the problem is that here behind this hyperechoic area, you have an area which is too dark and we can mix structures behind. Similarly, one has to remember that acoustic shadowing is not limited to grayscale. It can occur in color Doppler also. And then we get something like this, and which is an acoustic shadowing due to an aortic bryoprosthetic sewing ring. These are seen with strong attenuators. Be careful. You can miss structures behind. You can miss paravalvular leaks. So what do we go and how do we sort it out? We increase the aliasing velocity of color flow Doppler to have a closer look at the jet. We use different views, especially in Ts. We use the deep transgastric long axis view if we have to image the LVOT and aortic valve. And we can also do repositioning of the short axis aortic valve view to better image the leaflets. Acoustic enhancement, and this is something which is seen when we have a weak attenuator like a fluid filled cavity, and we encounter these problems many a times in the subcostal views. Weak attenuators are ones which attenuate at less than 0.5 decibel per centimeter per megahertz, and the problem is that behind that we get a hyperechoic area. So we see something which is too bright and we can assume it to be a fictitious structure, and it is as simple, just change the angle of ultrasound beam and you are sorted. Then we come to what is known as refraction, and the principle which is violated here is that the beam follows a linear path and uniform speed. That means that the beam which is being reflected back, so it can occur both from the transducer to the reflector and from the reflector to the transducer. At any time, if it passes through a tissue which sort of bends the wave, you get a false image as if this was the original direction of the wave. So you have a false image by the side of a true image, and this is a true aortic valve and this is a refraction artifact. So refractors again are pleura, pericardium, costal cartilage, facial structures and fat. And the ultrasound beam is refracted back. So what it produces is duplication of aortic, mitral and pulmonary valves. And it is as simple as just change and position of ultrasound beam. So,
no, tell me.
Okay. Then we come to what is known as the beam width artifact, and beam width is very common. This is the transducer. This is the beam width. It narrows at the focal point and then it diverges again and becomes weak. So we always presume the beam has a tubular vision, but if there is something in the wider range of the beam, which is a strong reflector and it reflects into the focal point, the ultrasound thinks that, oh, this is something over here, and since the time taken is from here to here, it plots something over here. So this is a false image which comes up. And one common example of beam width artifact is, again, I will say that it is not limited to grayscale. It can be seen in pulse wave Dopplers, continuous wave Dopplers, is a superimposition of a mitral inflow pattern in an aortic flow pattern. So there are ghost images of highly reflective objects which become visible along the same plane of real image. It produces intracavitary clutter and it is misdiagnosed as thrombus and masses. And it is very simple here. Just set the machine properly. Adjust the focal point or the focal zone towards an area of interest. Diminish gain so that reflections from the side area, the widened beam, are reduced. And of course, view in different acoustic windows from different angles. Side lobe artifact is again something similar, which violates the principle that echoes are generated only by reflectors which are located right in the main ultrasound beam. So here there are echoes which are generated by sides of the main beam, and when they meet highly reflective objects, they generate something like this, which are exactly like curves. So it produces intracavitary clutter. They are misdiagnosed as thrombus and masses, especially in LA and RA, and of course dissection flaps in the aorta. One common resolution for this is to use tissue harmonic imaging, which is a high frequency imaging, which amplifies the high energy signals which come from the center of the beam more than the low energy signals from the side of the beam. And now putting it together, one common problem which all starters everybody faces is aortic dissection. And we see a lot of shadows in both the ascending aorta short axis and the ascending aorta long axis, descending aorta long axis. So how to differentiate between the true flaps and the false flaps? So on the left is the true flap. They are always seen in dilated aortas. They have an independent motion unless a hematoma stops the motion. They have a constant echo intensity. And when there is, we put a color Doppler, there's a division of flow, a bifurcation of flow. And this flap respects anatomical boundaries and it cannot pass through the aortic wall. But when we look at false flaps, their reverberation and side lobe artifacts which produce the false flaps, the motion is parallel to the aortic valve or the sinotubular junction, the one which is producing the shadowing. Echo intensity diminishes as the flap moves towards the lumen. Color Doppler, the flow is not affected. It's the simplest thing. The color is there everywhere. And this flap may actually cut out of the aortic valve in some cuts. Now, coming to artifacts due to external equipment, it is very common. We have an external electric device and there is some problem with the ultrasound probe, and we get comet tails like this, which is an electrical interference artifact. And it is very simple. It goes off when you switch off the electronic device. When we use cautery, surgeons use, these are cautery artifacts. All of you are familiar with it. Just switch off the cautery. Again, cautery artifacts. The point to remember is artifacts can come in grayscale, in pulse wave, in continuous wave, in color Dopplers. So be very careful about it. And the last thing I want to highlight is what is known as the aliasing artifact. And in one word, when the jet velocity, the jet which we have transduced, exceeds the Nyquist limit on pulse wave, spectral, and color Doppler, that is when we get what is known as the aliasing artifact. I will just take some time on this. So when we have a pulse spectral Doppler, okay, so this is actually a jet here, and this is the negative side of the screen. We find that the high flow velocities are seen on the negative side of the graph. And when we put a color Doppler, we find that there is reversal of flow within the sample volume. Just remember the image. If you see something like this, this is known as an aliasing artifact. Now, what is the problem with this? The problem is that when you try to get the velocities, it gives you incorrect spectral Doppler velocities. And there is an advantage. It can be used in what is known as pizza to calculate the severity of valve regurgitation. Now, how do we resolve this when we see this on the screen? We use a lower frequency probe. We keep the object or the area of interest close to the probe, or we switch to what is known as a continuous wave Doppler. So on the same jet, if we use a continuous wave Doppler, which allows us to measure jets with higher velocities, but it does not permit us to locate the depth from which this jet is originating, it resolves the problem. So there is a slide I have put because in my life, I had struggled a lot to actually figure out what is this. So the aliasing velocity, that is the maximum velocity which the ultrasound beam can read, without getting into this artifact, is known as the Nyquist limit. And it is derived with this formula. The more important thing is, what is the Nyquist limit? It is the maximum change in Doppler shift frequency due to blood or tissue motion. That means the best your machine can do for you. What is PRF? It is, remember, it is the sampling frequency of the transducer. So if the transducer is firing 100 times a minute, the PRF will be 100. It is the sampling frequency of the transducer. C is the ultrasound velocity, and in tissues, which is 1540 centimeters per second. And F is the transducer frequency in megahertz. So, you can have 3 to 5 megahertz. Linear probes are 10 megahertz. Do not get confused between F and PRF. So this is the transducer frequency. This is the sampling frequency of the transducer. This is the angle of incidence of the ultrasound beam. So coming to a slide which is actually full of MCQs, the aliasing Vmax is known as Nyquist limit. Nyquist limit is by default in the machine half of pulse repetition frequency. 1 by pulse, the inverse of pulse repetition frequency is the pulse repetition period. So if my sample is transducer is firing 100 pulses a minute, the gap between the pulses will be the pulse repetition period. And if it is firing only 50 times a minute, the gap between them will be the pulse repetition period. And it is understood if you're firing only 50 times a minute, the period between the two firings is going to be much more than the period between 100 firings. And the pulse repetition period is always less than the time of flight, and the time of flight is the time it takes from the ultrasound probe for the beam to go and hit the object of interest and come back. So if my object of interest is very, very deep, my time of flight will be long. But what the machine does, it always keeps the pulse repetition frequency less than time of flight. And time of flight is decided by the sample volume and ultrasound velocity. So therefore, In one word, how do you knock off aliasing? Decrease the F. That means if you have a transducer with lower frequency, use it. Decrease the depth so that the time of flight reduces, so that the PRF reduces, and choose a structure whose velocity is less than Nyquist limit. Again, we have some artifacts. We all see click artifacts, opening and closing of native and prosthetic valves. And this is once in a while when we put a LVAD, and when there is a continuous flow, you will see these beams of continuous flow. You can't do anything for it except turning off the LVAD, which is not possible. And then there is a figure of 8 artifact. This is more from MCQ angle, and this is seen with the amp laser cardiac plug percutaneous LAA closure devices. So therefore, the carry home message from my side is recognize the artifacts. They are always linear, mostly linear, but they will generally not be in any anatomical shape. There are no clear attachments, while a true image will have attachments. There are no clear borders, while true images will have clear borders. They can pass through the walls of anatomical structures, while the true images cannot. Artifacts do not affect clear flow, while the true structures affect. The motion of an artifact will always be parallel or opposite to the real structure, while the true image will have an independent motion as per its anatomy. And an artifact will not be present in all other views, while a true image will be seen in multiple views. So therefore, when you decide to go in for an imaging, just plan, just don't take the machine and put the probe. See which structure has to be imaged, set the focus, set the depth, set the gain, set the angle, use color sensibly. Once in a while for endocardial borders and there's a problem, use tissue harmonic imaging, and always confirm what you see in multiple views. And other than the beginning, this is my last reference, is a beautiful paper, Fact or Artifact in 2D Echo, Avoid Misdiagnosis and the Missed Diagnosis. Thank you, and I'm done.